Hello, and thank you for taking the time to review ITOxygen's AIM Enterprise project. As you'll see, this project has been the culmination of hard work from our team, and we're very excited to show you everything we've accomplished over the past 2 semesters. Please note, some information visually has been redacted to respect the privacy of our sponsor. The goal of the AIM project was to deliver a prototype of a machine learning software that would receive welding data and then generate information that would assist the sponsor in making operational decisions. The sponsor wanted the ability to take information from any given welding machine and then be able to answer 2 questions. How much downtime is this machine experiencing? How consistent is that downtime? From there, further observations and data trends could be observed by our visualization outputs. To accomplish this goal, we needed to employ a design solution that worked for both our team and our project size. The solution that we came to ended up employing a mixture of Scrum's rapid prototyping and deployability frameworks, with an emphasis on the quick modeling. For this, we use visual aids to help guide our progress and maintain a clear logic flow. Below, you'll see some of those visual aids now.
As for the inner workings of our project, there are 3 key areas to understand: data computation, machine learning categorization, and visualizations. For the first, you'll note the values that we used from the data. To get down to this level, we filtered through a massive amount of information to reach only the key values required. This is to both save storage space, reduce calculation times, and limit the number of variables that impact the output. Next, we'll review our data computations. These are computed values that are not originally included in the dataset, but are important for us to make further analyses. These include downtime, whose formula you'll see, and duration, an inverse value of downtime. The next step in the project is to utilize machine learning to create useful categorizations, later referred to as clusters, as a way of quantifying frequency. To accomplish this end, we require the use of 2 tools: a data normalization scaler, which shrinks the range of values as seen, and a machine learning algorithm that can categorize an indeterminate number of clusters. A cluster, in this instance, is a set of downtimes that is deemed to be of equivalent or similar frequency. This concludes the logic that generates all important decision-making values. From this point, all of the data is visible in a CSV file that is generated at the end of this process.
Once core logic was implemented, it was time to invest in the user experience. As of this point, nothing was accessible outside of running an environment with hard-coded values. This would obviously be a poor user experience, one that would lend itself to a great deal of potential errors. To mitigate these issues, we made several advancements that allow for a more friendly end-user experience, regardless of technical capacity. To both accommodate user input and create a more visually appealing experience, we implemented the Qt-based UI system and bulk graphing. We chose the UI toolkit as the markup files it employs to show content allowed a basic level of Python scripting, which eliminated the need to introduce C++ to the project. In addition, the functions it had for generating page elements and transitions were relatively compatible with our visual output. As for the user input, we now allow for the user to input several items: an initial date range, which we refer to as device's baseline, a secondary date range, which we call the target range, and an industrial machine name, known simply as device. An additional custom date filtering function hides behind the secondary date, which allows for a custom date range pattern to be generated using the additional inputs below the top line's date range. Next, we review the graphing visualizer Bokeh. We chose the Bokeh Python library as it allows for a custom graphing experience that is more suitable for our project's needs. Per sponsor request, we needed the capacity to on-the-fly resize and rescale the viewport, which is baked into Bokeh's functionality. Additionally, it allowed us to expand graph functionality. As you can see below, we have 2 values on the legend in this graph. This is because it is a combination graph, containing downtime cluster data for both the baseline and target range of the user-selected device. With a single press, the user can hide either date range, allowing for a less visually noisy comparison of the 2 datasets. Now it's time for the final demonstration. We will simply go with the device that initially loaded, and then we'll pick a baseline. Finally, we'll fetch a report. In the background, the machine learning algorithm is currently running this date range over the downtime values associated with this device. We'll now see the output, which demonstrates the clustering we previously discussed. You'll note the areas above the blue dots. These are the key points that will be used in future observations, as they demonstrate variance from the expected downtime. Finally, we'll generate a target range, and see a comparison of the baseline versus the target range we just generated. In this instance, I'll be gathering dates from the next 2 weeks, and applying a week mask to only see dates from Tuesday and Friday. Now, we're looking at that final comparison. You'll note the ability to isolate one versus the other, but to ensure easy comparison, the baseline was given lower alpha values. This is the concluding segment of this video. We'd like to thank our enterprise leader and mentor, Nagesh, for all of his encouragement and feedback throughout this process. We'd also like to thank our sponsor for working with Michigan Tech's Enterprise Department to create this phenomenal opportunity. And finally, we'd like to thank you, the Design Expo judging panel, for taking the time to review our submission. Thank you.